Hello everyone, I am JoKo. I'm working with Future Mobile Communication Research Division at Atri. In this presentation, I'm going to present our views on 6G, mainly from a technology perspective. This is the outline of my presentation. I will first have a brief look at the recent trends of mobile communication-related services. Then I'd like to present our initial views on 6G, focusing on 6G direction and usage scenarios. Then I will discuss potential technologies for 6G radio access associated with 6G usage scenarios. Here we look at some of the services related with mobile communications that we think are important as future services around year 2030. Some of them have already started gaining popularity now. Some other services we expect will be realized and become popular in the future. Extended reality (XR) is a rapidly growing area. XR provides all real and virtual combined environments. Digital twin is a digital replica of a physical entity. An telepresence service people would feel if they are present at a place different from their true location. The post-industrial revolution, as it is well known, it requires fusion of all new technologies such as AI, robot, quantum computing, industrial IoT. A cyber-physical system is used to control physical processes in industrial applications. So we note that XR, digital twin, and CPS are quite similar to each other, in that these are the technologies dealing with the virtual world and real world, and combination of the two. And communications provide the interaction between the real world and the virtual world. Autonomous driving and flying vehicles will have their first appearance in 5G, but the full realization of autonomous vehicles may happen around year 2030 in the time frame of 6G. Efficient energy use is increasingly becoming important, and technologies utilizing energy harvesting and low energy consumption may enable user terminals without battery charging and also highly efficient, energy efficient networking. Regarding coverage and connectivity extension, mobile service coverage may need to be increased to include more unserved or underserved areas such as remote rural areas and non-terrestrial areas. And for those areas, not just rural connection, but broadband mobile service can be made available. Artificial intelligence. AI can be used for user-centric QoS management, self-optimization for radio access network and core networks. And even the design of air interface can be based on AI. Regarding reliability, privacy, and security, the important recent developments are DLT, quantum, and homographic cryptography. And the advancement of robotics will create robots that can obtain and handle information on behalf of humans, and also the robots that can engage in our life. Due to the emerging needs of private networking, non-public network is gaining popularity these days, and this trend is expected to be even more so in the future. Social networking service will evolve from simple text, pictures, and video clips to more vivid and live video contents with tactile internet. Now I'd like to share our views on 6G. First, 6G direction. 6G direction from our perspective can be summarized as follows. First, overcoming the limitations of 5G, and then promoting and spreading the integration and convergence of verticals. Regarding limitations of the current technology, there are four major areas that we think need to be addressed and improved in the future mobile communications. First one is latency reduction in wireline networks. In 5G, radio access latency was significantly reduced, but the overall latency in communication measured by end-to-end latency is not much different from 4G LTE. This is mainly due to the fact that most of latency occurs in wireline networks. So we need to cut down the latency not only in the radio link, but also in the wireline network. Secondly, going beyond the limits of existing technology for full realization of verticals. For example, industrial IoT, autonomous driving, or they are the representative verticals of 5G. But the full realization of such ultra-high precision services require high reliability, low latency communication, and high precision positioning that go beyond the current technology. Third one is artificial intelligence. Mobile communication systems are increasingly becoming complex. 6G mobile communication will be even more challenging, dealing with extreme complexity, massive traffic volume, diverse devices, and diverse services. So conventional solutions based on algorithmic approach will face serious challenges. Artificial intelligence can be a good solution in dealing with the complexity and diversity in 6G. Lastly, coverage extension. Up until now, the coverage of mobile service is mainly limited in the horizontal domain, on the surface or near the surface of the terrestrial area. 3D mobile communication extends the coverage into more vertical domain so that it can provide mobile service for aerial vehicles. And also recently, satellite communication is attracting lots of interest. And the primary goal of satellite-based radio access is to provide mobile service in unserved and underserved areas that cannot be properly covered by terrestrial networks. Now, in this slide, we discuss 6G usage scenarios. We describe a 6G usage scenario using usage scenario element, which we call in a shorter term usage element. Thus, usage elements characterize our 6G usage scenarios in terms of technology and service that 6G can provide with. Considering service trends and technology developments, we have come up with 6 usage elements, namely ultra broadband, ultra high precision, ultra large coverage, ultra high mobility, ultra massive connectivity, and ultra low energy. Our 6G usage scenarios can be schematically represented by a hexagonal cone as shown in this figure. So this is a 6G counterpart to the famous usage scenario triangle of 5G. To emphasize the importance of AI in 6G, we place intelligence vertex at the apex above the 6 vertices of the usage element hexagon. The intelligent vertex is connected with each usage element vertex. So characteristics of our 6G usage scenarios are: the first, the expansion and enhancements of 5 usage scenarios, which are EMBB, MMTC, and URLC. The second, new usage scenarios are provided as a combination of one or more usage scenarios, usage elements. In this slide, we show 60 KPIs associated with each usage element. For ultra broadband, the relevant KPIs will be peak data rate, user experience data rate, aerial traffic capacity, spectral efficiency. And these KPIs are similar to those of 5G EMBB case. So for ultra high precision, the KPIs are reliability and latency, positioning accuracy, clock synchronicity. For ultra large coverage, horizontal coverage and vertical coverage. For ultra high mobility, spectral efficiency at a given mobility, which is normally the speed of terminal. For ultra massive connectivity, volumetric connection density. Here volumetric means a three-dimensional space defined by a horizontal surface area and a vertical range above the surface. For ultra low energy, the KPI will be energy efficiency. Here we show some of the 60 use case examples together with the indication of associated 60 usage elements. For example, the use case in-flight broadband internet has two 6G usage elements, ultra-high mobility and ultra-large coverage. Now the remaining part of my presentation is about radio access technology for 6G. The first one is Terahertz communication. Terahertz radio access is defined as a radio access technology using a terahertz band in the frequency range of 100 GHz to 1 terahertz. Technical goal here is to achieve high speed, low latency, low power consumption by overcoming the limiting factors such as short propagation range and RF impairments in terahertz communication. Here are some important technical targets of our research on terahertz communication. And initially, we are going to characterize, investigate wireless channel properties, and look into RF impairments and their potential impacts on radio access. Then, considering all these investigation results, we are going to design radio access technology suitable for terahertz communication. So we think that we may need to revisit these basic elements of radio access technology, such as waveform, channel coding, synchronization, control signaling, etc. Similar to millimeter wave communication, terahertz communication needs to use multi-antenna beamforming for coverage and high spectral efficiency. Particularly, ultra-massive MIMO using a massive number of antenna elements can be an effective solution for coverage extension and spatial resource reuse. Also, multi-point MIMO can be used for creating artificial paths and thus providing high spectral efficiency for individual UEs. The connectivity control mobility supports also need enhancement, considering the propagation properties of this very high radio frequency and ultra-wide bandwidth. Important technical issues will include beam-based multiple access, handover control, ultra-wideband carrier aggregation, intra- and inter-beam interference control, and multi-connectivity, where multi-layered cellular networking is done using different cellular layers with the different spectrum bands, such as terahertz, millimeter wave, and sub-6 GHz band. Vertical services such as automotive and factory automation require low latency and ultra-reliable communication and highly accurate positioning. 5G, we think, is the first generation that enables high precision real-time control. Thus, it can support high precision vertical services. But for full realization of high precision services, further enhancements we think may be needed in areas such as URLC, time awareness, and positioning. For example, some isochronous real-time processes for factory automation require latency, reliability, clock synchronicity, and positioning accuracy that go beyond the current 5G. So for the complete replacement of wireline solutions in factory automation, we need higher requirements such as 10 to the minus 9 BRL, 0.1 millisecond user plan latency, and clock synchronicity of less than microsecond. In case of positioning, real-time high-precision positioning is necessary based on the requirements of industrial IoT. The required performance targets are set to be 10 cm for positioning accuracy and 5 milliseconds for positioning latency. Fortunately, as mobile spectrum is extended into higher spectrum areas such as millimeter wave in 5G and perhaps terahertz in 6G, ultra-wideband massive antenna arrays, high-density nodes, will become more commonly available in the network, thus providing a very good radio access networking environment for achieving such challenging goals. Next topic is 3D mobile communication. Until now, mobile communication has been mostly two-dimensional. The coverage is limited in the horizontal domain on the surface or near the surface of terrestrial area. 3D mobile communication extends the coverage into more vertical domain so that it can provide mobile service for aerial vehicles. This figure illustrates a variety of aerial mobile services. And here the main research topics will be 3D mobile networking, which is essentially vertical domain multi-layer networking, and 3D mobile transmission dealing with interference and new waveform. Our view for 6G satellite communication is the integration of terrestrial and satellite networks at the very first stage of 6G standardization. We call the integrated network one network. Currently, terrestrial and satellite networks are separated, and thus the user equipment needs separate modems to support the two networks. And also there are limitations in seamless service continuity due to the separation of the two networks. And also for the global coverage, the integration of terrestrial and satellite networks will be beneficial. For 6G satellite communication, one of the most important technical challenges is providing sufficient link budget for mobile broadband service, for which technology for both handheld user terminal and satellite payload needs to be developed. And another technical challenge is a vertical handover between terrestrial and satellite network. For ultra-high mobility, we target the support of gigabps data rate up to speed of 1000 km per hour. Here, technical issues will be dealing with high Doppler spread, antenna and cell deployments, and new modulation and waveform tailored for high mobility terminals. For ultra-massive connectivity, the technical areas we are looking at are twofold. First one is enhancements of traditional IoT, which requires ultra-low power, ultra-low cost massive IoT devices. Second one is support of usage scenarios, combining other usage elements, particularly support of massive connectivity and URLLC simultaneously. And another one is massive connectivity combined with aerial radio access. For ultra-low energy, zero energy networking utilizing ambient RF energy harvesting and backscatter communication will be promising. And this technology may enable zero energy IoT networking, particularly for short-range local networks. And for energy efficient radio access, we can use 3D beamforming, high density small cells, relay, intelligent node device one-off, which are actually what we have been doing in the past generations. AI can be applied to the areas such as mobile devices, mobile networks, and mobile edge computing. 6D mobile communications will introduce even more various IoT devices such as wearables and autonomous vehicles, as well as various types of smartphones, and the devices with AI features will provide a convenient world for humans. Introducing AI to these complex mobile networks will make it easy to optimize the management of radio transmission and networking. And AI can be applied to mobile edge computing, and this is expected to provide an intelligent mobile edge offering efficient application-based radio resource management for a variety of services. So this brings us to the end of my presentation. Thank you very much for your attention.